Okay, we're going to go ahead and get started. I still have people joining, so that's okay. I want to talk about tonight. We talked about last class. We talked about I gave you an introduction to AC circuits. So I want to talk about or show you a basic problem that you would do in AC, and then I want to talk about a couple other components. The main one tonight we'll talk about is a device called a capacitor. Tonight we'll talk about how capacitors are used in DC circuits, and then what I really want to get to is how they look when we put them in AC circuits by themselves, and how they look when we put them in AC circuits with resistors. So before we get into that, let's just review. We talked about the AC waveform. Let me forget that there's that. So we talked about the AC waveform as being sinusoidal in nature. So it looks like a sine wave. And I think last class we talked about some of the features of a sine wave, which you probably learned in your math class. Specific to this class, we talked about different values of AC. The important ones are the peak value, V peak, the peak to peak value, the RMS value, and the average value. This is also called the effective value. I'll just say be effective. And this is the one that's pretty important for us. So peak value, just from a graph, is what you would call the amplitude. So it's the maximum value on the sine wave. And then once you get the peak value, all of these other ones are calculated in terms of the peak value. So this would be twice the peak value. This would be 0.707 times the peak value. And this would be 0.637 times the peak value. So we talked about these equations. I don't think we use them a whole lot, but we talked about it. So if you had a basic problem with just resistors, notice the way I have this power source drawn. You've seen this before. That's, of course, that's a battery. But what you have over there is this. And that's an AC source. In this case, an AC voltage. So if you notice the way I have this written, I have a power source, an AC power source, and the value is 50 volts. I don't know if you can see that in the camera or not. That's 50 volts RMS. If given something like this, it's pretty simple to do. It's just Ohm's law, what you would expect. If I had a DC source there, you could go through and you can find, let's say, the current, the power, whatever you want. And if we did that, something I could ask you to calculate would be, like, maybe I want the current. So if I want to find current, current is equal to voltage over resistance. You got to look at what type of voltage I have. How's the voltage shown? Here it's in RMS. So this is VRMS. That will give you the current in RMS. And you just use it like you would as if it were DC. So 50 volts over 2K will give me 25 milliamps. But it's important to write the little subscript here, RMS, so I know what value I'm in. I could be in RMS, I could be in peak, peak to peak, and so forth. So these problems are pretty much like DC, and whatever I want, you could give me. If I wanted power, all the rules are the same. The fact that it's AC doesn't matter at all. If I wanted power, power would just be V times I. Now, in the case of power, you always want to use the RMS value for voltage and current to calculate power. We won't do a whole lot of that, but just to point it out, this is always in RMS. Given 50 volts RMS, I can ask you to give me the peak value for voltage. You should be able to get V peak to peak, V average, given given any one of these, you should be able to get the other. So we know that VRMS is equal to 0.707 times V peak. Well, if I tell you the RMS voltage is 50, this is 50, then you can solve this equation for the peak value. And once you get the peak value, you can give me the peak value because it's just 2V peak. And you can give me the average value because it's just 0.637 times the peak. So all of these equations I wrote on purpose in terms of the peak value. So once you get one thing, you can solve it for the peak value. You can use that to solve for all the other values. So all this stuff is pretty easy. It's not anything really important to wrap our minds around. It's pretty self-evident. Where this becomes harder is when I add other devices to the AC circuit. Now in DC, we only talked about resistors, but in AC, there's two other devices we'll talk about and we'll add to the circuit. So one is called a capacitor. We'll talk about what it is, but the symbol for capacitor is this. You may have seen this before somewhere. And the other is called an inductor. And an inductor is just basically a coil of wire, and it looks like this, the symbol. So once I add these to the circuit, especially if I have a resistor there, then it makes this stuff a little bit more interesting. So what I want to do tonight is we'll talk about this one. I'll give you homework, or actually it's already on Blackboard. I'll give you homework so you can practice with this. Now we're looking at this right now just from a DC point of view. And once you get familiar with capacitors, we'll look at how capacitors behave when I put it over here in the AC circuit. Then we'll do the same thing with the inductor, and then we'll put them all together, and we'll see the effect that that these devices have on the circuit. So I want to start with that. Start talking about this device called a capacitor. So capacitor. So what is a capacitor? A capacitor is a device that stores energy. Matter of fact, we'll talk about inductors. Both the capacitor and the inductors, both of them store energy. The main difference, other than physical differences, is where they store the energy. Capacitors store the energy in the electric field that exists between the plates of the capacitor. And as you'll see next when we talk about inductors store energy in the magnetic field that exists around the inductor. So capacitors store energy, but in engineering, we like to think of the ability to store charge. So these store charge. And why would we want to store charge? Well, why would you want to store anything? You store charge because, well, you store something because you want to use it later. And here you'll see that I can one application is to store energy or charge, and I can use that energy or charge later on if I need to. So let's talk about the capacitor. Physically, what is a capacitor? How does it look? Well, basically, a capacitor consists of two conductors separated by an insulator. So if I take maybe a metal sheet and another metal sheet, so this is a conductor, this is a conductor, and then between these conductors, I put an insulator. I put an insulator in between them. And usually what I do is I'll sandwich them together. This is like I heard somebody call it an insulator sandwich. It's like the first conductor, the metal plate, and I have a second conductor metal plate, and then between the meat would be like the insulator. By the way, when they call this insulator a dielectric. That's the dielectric. It just means insulator. So basically what they do is they take this maybe it's like some metal foil, and maybe you can use some wax paper, and you can then use another sheet of metal foil, and you can roll it up and put it in a case, and you got a capacitor. You're able to store charge or energy in that capacitor. So capacitors come in many shapes and sizes, and what I'm going to talk about tonight applies to what we call a parallel plate capacitor. A parallel plate capacitor. And there's usually just what I have here. We just show two parallel plates. And let me give you a formula to think about. And this describes some of the characteristics, shows the relationship between the area. Let me just put the formula on the board. We'll talk about it. So for capacitor formula I want to give you is this one. And I'll write the meaning of this down, but then I'll erase it. So go ahead, if you're taking notes, I'll give you a chance to write this down. I'm going to erase it, so make sure you do write it down. So the C stands for capacitance. And the capacitance is the device ability to store charge. The more capacitance it has, the higher the capacity to store charge. The C stands for capacitance. The unit is a farad. The farad. And that's a pretty big unit. So you're more likely to see microfarad and picofarad.
I can't hear you.
You can't hear me? Can you hear me?
For some strange reason, like I can see you, but I can't hear you.
Can anyone else hear me?
I can hear you.
Who can't hear me? Who was that? If you can't hear me, you might want to disconnect and try to rejoin, because I did have some issues earlier, but I think they got cleared up. The guy upstairs who shares my internet was using a TV, and that caused a problem, but I told him he couldn't do it now. So you might be having some kind of, if you can't hear me, I would say disconnect and then try to rejoin and see if that's better. If that doesn't work, you might have to call that number and call in to get the audio and use that pin. Okay? All right. So C is capacitance. The A, and I know it's a glare here on the board, so hopefully you can see this. This is the area of one plate. So it's like the cross-sectional area of one plate. So it's right here, the area, not of both plates, but just of one plate. And then this D is distance. That would be the distance between the plates. So from here to here, that would be the distance between the plates. And so area is in meters squared, and that distance would be in meters. Now you have a lot of decimal points here because the distance is like really tiny. So if you have that in meters, you're gonna have a lot of zeros, decimal points. Now the reason I'm pointing this out to you is that one of your homework problems, you actually have to use this equation. So I want to make sure that when you use this, that D needs to be in meters and the A needs to be in square meters. I think in the problem, they give this to you in square centimeters, they give this to you in meters. You can convert it over. If you don't convert it over, when you compare it to your answers, you'll see that they're off a little bit. But we'll talk about that when we get to that. So this formula right here is important to remember because it describes the physical characteristics of the capacitor. You can see, for example, that the relationship between the cross-section, the capacitance and the area of the plate, they're directly related. C is directly related to A. So the more area I have on the plate of the capacitor, the more charge I can hold. I make a smaller area, I can hold less charge if everything else stays constant. You see the relationship between distance and capacitance. It's just the opposite. This is the capacitance is inversely proportional to distance. So the more distance between the plates, the less capacitance I have on the capacitor and vice versa. Now, this K, let me remove some of this. Let's talk about K. This is called the dielectric constant. Dielectric constant. Somebody has their mic open. You guys can. Somebody has their mic open, and I know you guys can hear it. Can you tell whose mic is open? Okay, I just muted the mic, so somebody, well, I guess you can unmute it. I don't know. Can you guys still hear me?
Yeah.
Okay. All right. I'm learning this program. I didn't know I had the ability to do that, but I guess I do. So there is a homework problem based on this equation, so I do want to show you how to use it. I need to talk about this dielectric constant, this K, a little bit, because actually I don't have it. There's a little bit more to it. Let me get rid of this. So that dielectric constant K is really, let me see the value here. I don't remember it's really this constant. This is actually K sub epsilon. This is really the dielectric constant times some factor. I'll just call it for now. B. So I don't know what this factor is. This is a number constant. This is a constant value. And I can't remember the constant value right now. But what I do is I take that constant value and multiply by this K sub epsilon, which is this is the dielectric constant of a particular material. So I might have, let's say, I might have a piece of glass. Glass is an insulator. It'll have a certain dielectric constant. I always compare it to a vacuum or air. Basically, air you can have a dielectric constant of, let's say, 1. I don't know if it's 1, but it has a certain value. And actually, I think you guys have a chart with these constants on it. If not, I'll put it on the blackboard. So that you can actually look this up. But the point I'm making is when you look at your homework that I gave you, there'll be one calculation where you have to use this equation. And this K, they'll give you a number for it. So I'm showing that the number and the dielectric constant for whatever material they give you. I'm just representing that as this capital K here. You'll see it should be clear when you look at the work that I'm talking about. Other than that, you won't have to do any calculations with this. Mainly want you to see the relationship between capacitance, the area of the plate, and the distance between the plates. So this describes the physical characteristics of capacitors. Now what's important for us really is the electrical characteristics. We'll use this to understand how capacitors act in circuits in just a second. But let me give you this other equation. C equals Q on V. C equals Q on V. And I'll give you the definition of these. You might remember this right. Well, this of course is capacitance. But this right here, you might remember that's charge. So capacitance has the units of farads. The charge is in coulombs. So don't confuse this C with this C. This is capacitance, that's the symbol. This is the C, capital C, the unit. This is the unit. That's coulombs that will go along with charge. And of course, this is voltage. So the way to think about this is kind of like the Ohm's law for capacitors. Ohm's law has three symbols. I equals V over R. And in this case, we have three symbols. C equals Q over V. If I know the charge, I know the voltage across the capacitor, then I can get the value of the capacitance. So we'll use that. But before we get to using that, I want to go back to this and that relationship that I pointed out to you between C and A and C and D. Now, if you're taking notes, I want you to write something down. What I want you to write down is this. Charge for capacitor behaves like current for resistor. I'll say it again. Charge for capacitor behaves like current for resistor. Now, what does that mean? Well, just say I have resistors in series. R1 and R2. And I got capacitors in series. Here's the way you draw a capacitor symbol. C1 and C2. What we learned about resistors in series and current is that if current flows into this circuit, since there's only one path of current, the current is the same everywhere. So if I say the current is 5 amps, it's 5 amps everywhere in the series circuit. Well, that's true of charge in the capacitor circuit. If I say the charge Q equals 5 coulombs, which is a lot of charge, then it's 5 coulombs everywhere. So whatever's true for current in the resistor circuit is true for charge in the capacitor circuit. So here, resistors in series, the current is the same everywhere. Here, capacitors in series, the charge is the same everywhere. Well, what about if I put the resistors in parallel? How does that change things? If I have the resistors in parallel, R1 and R2, and I put the capacitors in parallel, C1 and C2. Now, in this case, whatever voltage I have across this circuit, whatever voltage I have, what we learned about things in parallel, the voltage is the same everywhere. And that's true over here. I have a voltage across the circuit. Whatever the voltage is, it's the same everywhere. So if this was, let's say this was 10 volts, I would measure 10 volts across both resistors. If this was 10 volts, I would measure 10 volts across each capacitor. But the charge is what I told you to think about. So here, if current is flowing here, let's say I got the total current here, this will get a certain amount of current, I1, and this could get a certain amount of current, I2, and the total current will be the sum of these two. Well, what's true for current and resistor circuits is true for charge and capacitor circuits. This will get a certain amount of charge. It'll charge up to a certain level. I'll just call it Q1. And this will charge up to a certain amount of charge. We'll call this Q2. The total charge in the circuit will be the sum of these two, just like the total current in the circuit is the sum of these two. So again, I say it, the charge in the capacitor circuit behaves like current in the resistor circuit. So that's the first thing to remember. Now, it does get a little bit confusing when we talk about capacitance. So let's talk about capacitance and how capacitors behave when they're hooked in series and parallel. So I want to start by let's look at resistors in parallel. So let's say I got two resistors. A 6 ohm and a 3 ohm. I want to find the total resistance. But then I give you the same problem, the same exact problem. I'm going to change these from resistors to capacitors. So over here I got capacitors in parallel. We'll use these same numbers again. I'll just put it this way. This is 6, I'm going to say microfarads, because a farad is a big unit. And this is 3, that might be in the glare spot up there, so I'll put this off to the side. This is 6 microfarads, and this is 3 microfarads. So I got the same exact problem. Over here I use resistors, and over here I use capacitors. And what I want to find is RT, and in this circuit I want to find CT. So how would I do it? Well, we all know how to do this one. That's easy to do. What I do, I use one of those formulas. I gave you two. I gave you product over the sum. I gave you the reciprocal formula. Because these numbers are so easy, I can just let's use product over the sum. If I want to find the total resistance, it's just the first resistor by the second resistor divided by the sum of the two. So you would say, all right, I got 6 ohms times 3 ohms over 6 ohms plus 3 ohms on the top. Again, I'm getting in that spot up there where you can't see. So on the top here, 6 times 3, I get 18. So I get 18, and on the bottom, 6 plus 3, I would get 9. And I divide this, I get 2 ohms. So the total resistance is 2 ohms. And notice that in the parallel circuit, we said the total resistance will always be smaller than the smallest resistor in the circuit. So this is 3 is the smallest one. I expect the total to be less than that. And it is, it's 2. But now how will we do this? Well, it turns out that capacitors in parallel act like resistors in series. I'll say it again. Capacitors in parallel act like resistors in series. So I don't use this formula. I use this formula. I use the fact that capacitors in parallel act like resistors in series. So the total capacitance here is going to be C1 plus C2. So there in parallel, I have to add them up. Just like I have resistors in series, I would add them up. In this case, the total capacitance is going to be 6 microfarads plus 3 microfarads. I'll get 9 microfarads. So what I want you to remember from this example, the takeaway is what I said, capacitors in parallel act like resistors in series. If these resistors were in series, I would add them up. I wouldn't do all this math right here. I would just add them up and get 9. Now, why is that? Why is it that the more capacitors I add in parallel, the bigger the number I get over here? What am I doing physically to cause this to happen? And that's the reason why earlier I started talking about these relationships. Let's go back to what I said earlier. We said that capacitance is directly proportional, directly related to the area of the plates. That came from this formula, C equals K A over D. C and A are directly related. So let's have two capacitors hooked up like this. I got capacitor C1, I got capacitor C2, and they're hooked up in parallel like that. What am I doing physically to increase the capacitance? Well, pretty simple. When you look at the makeup of a capacitor, this capacitor, what I have, you see the capacitor is a basically plate of metal or conductor. So let's say this first capacitor, C1, I got plates for that one. Now in between, I'm not showing the dielectric, but there's a dielectric between it. So this is C1, and the capacitor C2. And let's say the area of this and the area of this are the same, just to make it easy. So each capacitor by itself looks like that. C1 is two plates of two conductors separated by a dielectric, and C2 is two conductors separated by a dielectric. But when you do this, when you put a wire from here to here, effectively what you're doing is you are connecting a wire from this first area plate over to the second area plate, and that's equivalent to taking these two plates and moving them together like this. A from the first one and A from the second one. If those two areas are equal, then you've just doubled the area. If you double the area here, if I put a 2 here, then the capacitance or the device's ability to store charge is going to double. You physically made more room for charge to go into the plate of the capacitor. So it makes sense here, if you think about it from the point of view of area, that the more plates I have in parallel, the more capacitance I have. And this is the reason why capacitors in parallel act like resistors in series. The more capacitors I put in parallel, I keep adding the capacitance up to get the total capacitance. So that's the first thing to wrap your mind around. Capacitors in parallel act like resistors in series. You just add them up. Now, what about the other situation? I go back to my same two resistors. But this time we're going to put them in series. So I had a 3 ohm and I had a 6 ohm. This was R1, this is R2, and I'll do the same with my capacitors. I had C1 and C2. This is 3 microfarads and this is 6 microfarads. And in both cases, here I want to find the total resistance, and here I want to find the total capacitance. So how would I do that? Well, this is really easy. We know that resistors in series, I just add them up. We learned in class that for this circuit, RT is just the sum of R1 plus R2, which in this case is 9 ohms. So that is easy to do. Well, capacitors in series act like resistors in parallel. Capacitors in series act like resistors in parallel. So in this case, when they're hooked up in series, that's when I want to use the product over the sum rule. With resistors, it was the total resistance equal R1 times R2 over R1 plus R2. We're going to change the R's to C's. So when I have capacitors in series to find the total, it'll be C1 by C2 over C1 plus C2. And so for this one, I would have, put the numbers in, I get 3 microfarads, 6 microfarads over 3 microfarads plus 6 microfarads. So my total capacitance here would be 2 microfarads. So I'll say it again, capacitors in parallel behave like resistors in series, and capacitors in series behave like resistors in parallel. So notice when I have them in parallel, when I have them in series, the more capacitors I have in series, the lower the total capacitance is. And you might think to yourself, well, why is that? What's causing the capacitance to drop? And again, I go back to that relationship that we talked about at the beginning of the lecture. The relationship between C and D was like that. The greater the distance between the plates, the lower the capacitance. And you say, all right, well, we're not really changing the distance between the plates. How does that apply to this? Well, let me show you. Suppose we had 3 capacitors. Now, the way you draw capacitors like this, right, but I want to draw it like this, just to represent the plates. Now, be careful, because this actually has another meaning in electrical engineering. This is actually a contact for a relay. Well, in the old days, they would draw capacitors like this. So I'm going to go back to that and use this for a capacitor, because this reminds you more of a parallel plate or conductors or pieces of metal than that does. So I want you to think about me having 3 capacitors in series. I'm going to hook them up in series. So I got my first one. I got my second one. And I got my third one. And I'm going to hook them up in series. So this is C1, this is C2, and this is C3. Then what I'm going to do is I'm going to put some charge in here. I'm going to send current into here and charge it up. So I'm sending charge. Now remember, what current is charge per unit time. So I'm actually sending some charge to the capacitors, all the capacitors. And since this is a series circuit, they get the same amount of current. And we said that current in resistor circuits and charge in capacitor circuits are the same. So if this gets the same amount of current, what that means is that each capacitor gets the same amount of charge. So whatever charge is on this one, that same charge is on every capacitor that's connected in series. So I'm just going to draw charge like this. When it's charged, I have some plus charge on one plate, and I'll have minus charge on the other plate. When the capacitor is charged, this is what the plates look like. One will be charged positively, and the other will be charged negatively. So I'm going to show that like this. Say this charge is up, and I'm just going to show 3 positive charges here. And then I have 3 negative ones here. If that capacitor was charged, that's what it would look like. Now, if I have 3 on each plate, that means it's the same everywhere. So I would have the same amount of charge here and here, same here and here. So what I'm showing is the plus and minus charge, the separation, is the same on each plate of the capacitor. Now, I don't know how well you can see this in that camera, but if I circle in here, this region in here, if you focus on that region in the circle, you will notice something. You'll notice that I have basically this situation where I have positive and negative charge, and they're able to get together through a wire. What I'm saying is, I got 3 negative charges here, I got 3 positive charges here, and when I put these in series, I actually connected a wire between the two plates. So these charges can get together. Well, you know that if I have 3 positive charges and I add to it 3 negative charges, what I'll get is 0 charge. So basically, I got 3 negatives and 3 positives. They can come together through this connection. And on the bottom here, I have 3 negatives and 3 positives. They can also move through that wire and come together. So basically, all the charge inside of this circle cancels out to 0. It cancels out to 0. And the significance of that is, and this is a little bit hard to think about, but the significance is this. What you've done is you've increased D. Not physically, but electrically. You've increased the D. And if I increase D, then the capacitance will go down. The device's ability to store or hold charge will drop. And that's what you saw when I have this in. I had the 3 microfarads, and I had the 6 microfarads, which had the total CT came out to be 2 microfarads. The more I add in series, the smaller that the total is going to be. I'm lessening or reducing the ability of the device to store charge. So that's an explanation. But again, it's good to understand that. But the main takeaway is this, that capacitors in parallel behave like resistors in series. Capacitors in series behave like resistors in parallel when I want to find the total capacitance. And then the other thing I said is that current for a resistor and charge for a capacitor, you kind of treat them the same way. So whatever's true for current for a resistor is true for charge for a capacitor. In a series circuit with resistors, the current is the same everywhere. Well, that means in a series circuit with capacitors, the charge is the same everywhere. In a parallel circuit with resistors, the current in each resistor adds up to the total. Well, in a parallel circuit with capacitor, the charge in each capacitor will add up to the total charge. So let me put the formulas on the board, and then I want to work a problem based on the relationships we just talked about and the formula that I gave you earlier. So if you're making an equation sheet, here is what you want to write down. These are the formulas that you'll use to do DC analysis with capacitors. So the first one was this. C equals Q. Let me put it over here. C equals Q on V. So this is like our Ohm's law here. We'll use this. And this is true if I have only capacitors in the circuit. If I have a resistor in the capacitor, this isn't valid. But if I have if I have a circuit with only capacitors, then I can use this formula. C equals Q on V. Capacitance equals charge over voltage. That's one formula. And then the other one you'll need, if I want to find the total capacitance for capacitors in parallel, the total, I will just take each capacitance and keep adding it. So I'm just going to draw it like this. That keeps going and going and going. So make sure you write in your notes, this is for capacitors, caps, in parallel. They act like resistors in series, I just add them up. And then finally, I will use either this one, CT equals C1 over C2, C1 plus C2, and this is for capacitors in series, caps in series. They act like that. Well, when I showed you the problem, I only showed you C1 and C2. I showed you C1 and C2, and C1, C2. What if I have another one? C3 or C4. When I keep adding them, then this wouldn't work anymore. Well, if you remember, when we did resistors, I gave you for total resistance in parallel, it was R1 by R2 over R1 plus R2, which is kind of an analogy to what I got here. But I also gave you that 1 over RT equals 1 over R1 plus 1 over R2, and I keep adding them up like that. So you can use this one if you have more than one capacitor in series. So I write it in terms of capacitors. 1 over CT equals 1 over C1 plus 1 over C2, and that just keeps going. So if I put that over here neatly, CT and that just keeps going. All right, so here are the formulas we have to work with. And And what I'm going to do now is put a circuit on the board. Now, I don't have a calculator, so you guys will have to help me calculate. Now, I'm going to put a circuit on the board, and we'll work it out as an example. And you'll see, matter of fact, I think it's the first problem on your homework sheet. So I don't know if you printed that out or not. If you did print it out, that's fine. If you didn't, it doesn't matter. We can print it out later. But let me put the first problem on the board, and we'll work this as an example. Yeah, I gotta put my glasses on. These prop numbers are so small. All right. All right, so I got 80 volts, and that's my total voltage. I got C1, that's 0.02 microfarad. So you guys write this down, get a sheet of paper and work along with me, please. Draw a circuit out, and this will be a good practice for your homework. Now, on the homework, you can't see it on the camera. It's actually 2 sheets on Blackboard. But I give you these problems. There's 1, 2, 3, 4, 5, 6. There's 6 problems, but we're doing the first one here. So you really only got to do 5. But on the back of this sheet, you probably can't see it in that camera. But I put a big X through here. At the top are the answers to the odd number problems on the front. So when you do this homework sheet, you can check to see if you're doing it right. Now, you don't know which one I'm going to grade. I'm just going to pick one out of the whole sheet, and it won't be the first one because we're doing it. But that's how I'll grade this. You got to get them all right because you don't know which one I'm going to grade. So this is capacitor homework number 1. And again, the answers on the back. On Blackboard, I had to scan 2 separate sheets. So you'll have one sheet that's called capacitor homework 1, and in the back that has the answers to the odd problems, they'll say capacitor homework 1 answers or something like that. It'll be clear on Blackboard when you go there. So C1 is 0.02 microfarads. This is 0.05 microfarads, and this is C3, and this would be 0.1 microfarads. So let me show you what we got to find for this. I'm going to erase this, so hopefully you got this down on some paper at your desk or wherever you are. And what they want us to find basically is they want us to find the charge for each capacitor and the voltage across each capacitor, given the value of each capacitor. They want us to find charge, and they want us to find the voltage. And the way we're going to do that is we're going to make use of the formula C equals Q on V for the whole circuit and for each capacitor individually. So how would we work a problem like this? Well, the way you would do this is exactly like you would take the same approach that you would take if these are resistors instead of capacitors. I could give you 3 resistors in series and say, I want you to find the current and I want you to find the voltage across each resistor. Here I'm asking for the charge and the voltage across each capacitor. Remember we said charge for a capacitor is like current for a resistor. So just imagine that these are resistors. And you have 3 resistors. You know all the values of each resistor. And I say, all right, find the current and find the voltage across each resistor. You would use Ohm's law, and the first thing you would do is you find the total resistance. You find the total resistance. The second thing you would do is you use that resistance to find the total current. You say I equals V over R. And then you would use that current to find the voltage drop V equals I times R for each resistor. You do exactly the same thing for this circuit. Exactly the same. So I'm going to take my time and go through this, and we'll work it out. We'll follow this logic. Instead of finding RT, I'm going to find CT. Instead of finding I, now this is like CT. We're going to find CT. And instead of finding IT, for capacitors, we're concerned with QT. And then we can find each voltage for each capacitor. So we're going to follow the same exact logic that we were following, that we learned about when we learned about resistance series. So let's go ahead and do that. So given a circuit of capacitors in series, and you know all the values, then what you do is you'll find the total capacitance. We got to find CT. What you remember is what I said earlier, capacitors in series act like resistors in parallel. Capacitors in parallel act like resistors in series. So I see I have capacitors in series. They're going to act like resistors in parallel. And what do I mean, act like resistors in parallel? Well, resistors in parallel act like this. 1 over RT equals 1 over R1 plus 1 over R2, and they keep going like that. So we got to write the total capacitance like I would write total resistance if I had parallel resistors. So the formula is going to look like this. 1 over CT is going to equal 1 over C1 plus 1 over C2 plus 1 over C3. Capacitors in series act like resistors in parallel, and this is like a formula I gave you for parallel resistors. So what you got to do is put these numbers in here, and we got to solve that for CT. Now, I don't have a calculator, so I think it's like 4 or 5 of you out there. So take out your calculators. You're going to have to help me calculate, but I'll put the numbers in. And what I'm going to do is, they give me these values. I'm just going to put these in, and we got to solve that for CT. And these are all in microfarads. So just to keep this board clean, and I don't have a lot of room, I'm not going to write the microfarads. I'm just going to write the numbers. And whatever I end up with, that answer will be in microfarads because these are all in microfarads. But C1 is 0.02 microfarads. C2 is 0.05 microfarads. And C3 has 0.1 microfarad. So I need for somebody to take a calculator and give me, I showed you how to use a reciprocal key. Give me the value for CT in that formula.
It's 0.0125.
So the total capacitance CT is 0.0125, and that's capacitance, so it would be microfarads. Microfarads. So make sure you see how he got that, 0.0125 microfarads. Now that I know the total capacitance, I can use this formula right here. CT equals QT on VT. And I know this, that's just this, they gave that to us. And I know this, because we just solved for it. All I got to figure out is this. So let's put that into the equation, and we'll figure out what that is. So notice the steps. I want you to write down the steps. I know all the value for the series connection of capacitors. The first thing we did was find the total capacitance using the formula here. We came out with this number. So right here, I can get rid of this, and I can put in 0.0125. And again, this is microfarads. I'm not going to put the units. I should, but whatever answer we get will be in micro. So I'm just going to put 0.0125. So I know that number. I also know VT. VT is 80 volts. So I can put in 80 there. And the only unknown here is QT. So somebody figure out for me, what is QT? What is it?
1.
1. So QT, I don't know, is that glare? Can you guys see about right here? Or is it a glare? Can you see that? Can you guys see this?
No.
All right, let me move it down lower. Let me get a chair. I might have to get down real low, and I'm too fat to get down without a chair. All right. So CT, we said that was 1, but remember, since this was all in micro, it's actually 1. That's not CT, it's QT. QT. QT came out to be 1. Now that's charge. So charge is in coulombs. It'll be 1 microcoulomb because this was in microfarads. I just didn't put the little U thing in there. So now we know that I have 1 microcoulomb of charge in the circuit. Now, what does that mean, 1 microcoulomb? Well, remember, okay, go back to what I said earlier. Charge for capacitors act like current for resistors. If these are resistors, they're in series, the current will be the same everywhere. Well, these are the capacitors, so the charge is going to be the same everywhere. So if I know that I have 1 microcoulomb of charge, that means right here, I got 1 microcoulomb. Right here, I got 1 microcoulomb. And right here, I got 1 microcoulomb. The charge in the series circuit is the same everywhere when I deal with capacitors, just like the current in the series circuit is the same everywhere when I deal with resistors. So finding the charge anywhere, I found the charge everywhere when I have capacitors in series. So I got more information now. So the only thing I have to do is figure out the voltage across each capacitor. And again, I go back to this equation. I keep using the same equation over and over again. I go back to C equals Q on V. But this time we're going to do it for each, we did it for the whole circuit before to get the 1 microcoulomb. Now we're going to do it for each individual capacitor to get the voltage across each capacitor. So what I'm saying is this. C equals Q on V. That means V equals Q on C. So that's how I get voltage. So I want the voltage for each and every capacitor. So I named the voltage across capacitor after the capacitance. This is C1, the voltage across it is V1. This is C2, the voltage across it is V2, and so forth. So V1 will equal Q divided by C1. V2 will equal Q divided by C2, and V3 will equal Q divided by C3. Again, this is why I call this the Ohm's law for capacitors. I keep coming back to this and using it over and over again. I can use it for the whole circuit, like I did in the beginning, or I could use it for each individual capacitor, like I'm about to do right now. So let's do the first capacitor. But the first capacitor, Q, well, we said Q was Q is 1 microcoulomb, I'm sorry. Q is 1 microcoulomb, so I got 1 microcoulomb divided by C1. Well, C1 is 0.02 microfarads. 0.02 microfarads. Now notice, I got micro over micro, so they're going to cancel out, which is nice. So what's 1 divided by 0.02? What is
50
that?
volts.
I got 50 volts. I'm going to in here take my coloring pencils, 50 volts from there to there. And I'm going to do the same thing here. I got 1 microcoulomb coulomb divided by 0.05 microfarads. What's 1 divided by 0.05?
20 volts.
20 volts is correct. So I got 20 volts. Now at this point, I can do the same thing. I can say, all right, I got 1 microcoulomb divided by 0.1 microfarad if I want to. Or remember Kirchhoff's voltage law? Kirchhoff's voltage law says that if I have resistors in series, the voltage drop across all of them have to add up to the total. Well, that not only works for resistors, it works for anything. I don't care what you have. If it's hooked up, it's got voltage across it, the voltages have to add up to the total voltage. So if I have a total of 8, this is 50, and that's 20, 56, that's 70. This has to be what?
10.
This has to be 10 volts. I guess I'll put it in here. And it's solved. Now, this is actually not a bad problem. The thinking is a little bit different. We said resistors, capacitors in series act like resistors in parallel and vice versa. But other than that, this is exactly what you do when you work with resistors. So it shouldn't be too bad. Now, you have a couple of these on the homework. You got like 1, 2, 3. There's 4 like this. And we just did one of the 4, so there's like 3. You should go ahead and show this on the homework, but this is just to show you how to do it. But then you get to a problem like this. And I'm not going to do it. I just want to show you how to do it. So I'm going to erase this. You can always play. I'll put this on YouTube, so you can always play it back and rewatch this. But they give you one like this. To give you one where they give you the voltage. And they give you some capacitors. C1, C2, C3. But then they gave you something like this. Now you got C4. And tell you to do exactly what we did in the last problem. Find all the voltage across all the voltage drops across each capacitor. So what would you do? Well, what you would do is actually pretty simple. What you would do is, think about what you would do if these were all resistors. If these were all resistors, you say, okay, I got these 2 resistors in parallel. I'll combine them into one and get one equivalent resistance, and now I have a series circuit, and then I'll solve the series circuit. Well, that's exactly what you would do here. You would actually redraw this circuit like this. I got C1. Now this one right here, these 2 are in parallel. You got to remember, when I have capacitors in parallel, it acts like resistors in series. Resistors in series, I add them up. So capacitors in parallel, I would add them up. So the value of this would be C2 plus C4, whatever that is. When you add them up, that's what you would put here. And then you'd have this capacitor, C3. You would have that circuit. And this is exactly the circuit we just got through solving. So you would just combine these to get a series circuit. And then you would solve this exactly like we did in the problem we just got through doing. And what that will do is give you information about, you'll have the voltage drop across each of these. So by solving this, you will know the voltage. Let me get a green marker. If you solve that, you will get the voltage across this one, V1, which means you would know this. Then you will get the voltage across this one, V3, which means you would know this one, V3. But then when you get the voltage across this one, this V, this is the combination of 2 and 4, you get that voltage. That voltage is actually across both of these because they're in parallel. But it doesn't matter because for each resistor, you will now know you're given the capacitance and you will know the voltage, and you will just use C equals Q on V. You know the voltage, you know the capacitance. You can find the charge in every capacitor here. So the trick is, or the secret is, combine this down to a series circuit, solve the series circuit, and put the information back in the original circuit, and look for what's unknown here and solve for that. So just try it out. Again, I give you like 6 problems, and the last one, number 9, is kind of a tough one. I mean, it's not really tough. It's just more capacitor. But I also have a worked out solution. So I'm going to let you guys, work with this for a little while. And if you get stuck on number 9, I can probably put a solution sheet up. But hopefully you won't get stuck on it because I want to grade number 9. I might grade number 9. So we'll see. That's already available on Blackboard, though. If you didn't get a chance to look at it, you can go look at it after the video. And you got all the documents up there for that. Now, I'm not done. I want to talk about a couple more things, and then I got a couple things, loose ends we need to tie up before we sign off of here. I'm trying to see if I actually want to. Let me say a little bit about it now, and then I may pick up some of this in the next video. We'll see. So this is one kind of calculation you got to do for capacitors. Now there's something else, and this is actually kind of cool. You might like this. So I want you to think about this. If I have a battery, and I have a switch, I have a resistor, and I got a capacitor. And here's my voltage, here's my resistance, and here's my capacitor. This is called an RC circuit. RC circuit. And I want to talk about how this circuit behaves. What happens when I close the switch? So what we're going to do is we'll close the switch, and when I close the switch, I'll tell you what's going to happen. When I close the switch, the capacitor is going to start to charge up. It's going to get more and more and more volts across it until it equals what's over here. When I close the switch, the very instance I close the switch, I'm going to call that T0. This is the instance switch is closed. This is a time. T0 stands for the instance the switch is closed. So that's a time, T-I-M-E, time. Let's look at what happens when I do this. I'm going to put some values over here. I don't really need one over here yet. But so I'm going to close the switch. And then T0, the instant I close the switch, there is no charge in the capacitor. So there's no charge in the capacitor. The reason there is no charge in the capacitor is because it takes time, T-I-M-E, it takes time for that capacitor to charge up. The reason it takes time is because I got a resistor in front of it. The bigger resistor, the longer it's going to take that capacitor to charge up. It's kind of like a bathtub, and this is a spigot. The more resistance I have in that spigot, the smaller the hole, the longer it's going to take for that bathtub to fill up. Instead of water, what we're controlling is current, the flow of current to that capacitor. and the current is nothing charged in that capacitor. So when I close the switch at t equals 0, there's no charge in the capacitor. Now for a capacitor, as the charge builds up, the voltage builds up. So let's say that this is 10 volts. The battery is 10 volts. And I don't have any charge to begin with in the capacitor. I close the switch, t equals 0, t0. The instant I close the switch, there's no charge in the capacitor, which means there's no voltage across the capacitor. Well, Kirchhoff's voltage law is valid. Kirchhoff's voltage law says the voltage across the resistor plus the voltage across the capacitor has got to add up to 10. Since there's no charge in the capacitor, there can be no voltage across the capacitor. That means the 10 volts has to appear across the resistor. I got 10 volts across the resistor. But then the clock starts to tick. I go T0, and then this thing starts to charge up. I start to dump current or charge into the capacitor, so it starts to charge up. So let's say the capacitor charges up to 1 volt. It now has charge in it, enough charge to produce 1 volt across the capacitor. Well, if I have 1 volt, the only way I can have this 1 volt and not violate Kirchhoff's voltage law is if this is 1 volt, it has to drop down to 9 volts. And this will charge up to 4 volts. Let's say it charges up to 4 volts. Well, that's 4. That means that this is dropped to 6 volts. Eventually, this will reach 8 volts, which means that this has to drop to 2 volts. And eventually, this will charge completely up. I'll get 10 volts across my capacitor, and that means the voltage across the resistor now is 0 volts. I fully charged the capacitor. At that point, what you can do if you wanted to, at that point, you can take this out of the circuit and set it over here. It's got charge stored in it, and it's got 10 volts across it. You can take it completely out of the circuit and set it over here, and it's storing charge for you. So 2 things kind of cool about this. Number 1, the whole idea that I'm storing voltage or charge in this device. You just set it on the shelf, and you got charge. You can get it and use it later for something. That's kind of cool. Kind of acts like a battery, but better, because I can charge this up as fast or as slow as I want. I can't do that with a regular battery. The other cool thing about it is the fact that it took a while for this thing to charge up. It turns out that we can actually control how fast or how slow this thing will charge up. And that has a ton of applications. There's a lot of reasons why you want to do that. So let me talk a little bit about that. I want to erase the circuit and move it over. And let's look at this in a little more detail. So let me redraw my circuit. All right. Now, let's start by looking at the product. If I take R times C, I want to know what will I get? What kind of thing is this? What kind of physical quantity will I get by multiplying the resistor value by the capacitor value? So the way we'll do that is we know that R equals V over I, and we know that C equals Q on V. We just learned that today. So knowing that, what I can do is I can substitute into this equation these values. It look like this. R times C equals question mark. Well, that R right there from Ohm's law is equal to V on I. And then C is equal to Q on V, according to this. If that's the case, you can see right away what's going to happen. These two V's are going to drop out. And that will mean that R times C is really equal to Q on I. By taking R times C, I get this thing Q on I. But okay, what's that? What is Q over I? What kind of thing do I get? Well, you got to go back to the first week of class. We talked about current. We said current is charge per unit time. In other words, I equals Q on T, where that T is time. So what I can do is for that I can get rid of that and put in there the fact that it's equal to Q on T. What is that when I cancel out things that need to be canceled out? Well, let's do it. If I take this Q divided by this Q on T, what I really got to do is take that Q times T on Q. When I do that, the Q's cancel, and I end up with T, which is time. So what are we saying? Well, what we're saying is, when I take the product of R times C, what I get is time in seconds. I get time in seconds. So for example, let's say that this resistor value is 1 megohm. And let's say that the capacitor value is 10 microfarads. And I can apply what I just learned right here to that circuit. I would say that R, which is 1 megohm. Now 1 megohm is 1 times 10 to the 6 ohms. So I'm multiplying that by 10 microfarads. That's 10 times 10 to the minus 6. That's micro, minus 6 farads. I'm only writing it out this way so you can see what happens. We can clearly see right here, I get 10 to the 6. I get 10 to the 6 times 10 to the minus 6. That's 10 to the 0, which is 1. So basically, when I multiply this times that, I can just cancel those out. They're gone. It's just a 1. So to get my answer, I take 1 times 10. What I get is 10 seconds. So this is 10 seconds. Now what's the meaning of the 10 seconds? So I want to explain that. And then we'll probably, I'll explain this and I'll probably go ahead and this will be it for today. And then I'll say more about it next time. What's the meaning of the 10 seconds? Well, let me go back to this RC thing. I'll give you some new vocabulary. I just showed you that the product of R and C is time. It's time. So what they do, this product right here, they call that a time constant. They call it a time constant. And the way they represent it is like this. So this is what we call a time constant. It's nothing, it's just a name. It's just a name for this product, a time constant, no big deal. And they use this is the Greek letter tau, to represent a time constant in the RC circuit. So here, this tau, this right here, that value is tau. Tau equals 10 seconds in the circuit we just got through for the example problem. Where this is important is this. What happens in a capacitor when you charge it up? I want you to think about how this would work. When you close that switch, initially there's no charge in the capacitor. Now you remember from the first week of class, we said like charges repel, unlike charges attract. So let's say I put some positive charge. I don't have any charge at first, so positive charge comes in here. And then when the next charge comes in, I got like charges repel. It's going to be kind of difficult for this to get on the plate because I already got positive charge on the plate. But let's say it makes its way on the plate. Now the third charge comes on the plate. Now it's twice as hard for the charge to get on the plate because I got two other charges sitting there pushing against it. The more charge I dump onto the plate of the capacitor, the harder it is for the next one to get on. So you can probably see how this is going to work. It's going to be really easy in the beginning for the charge to flow through the capacitor, which means you're going to have a lot of current flowing in at first, but then as it fills up, it's going to fill up slower and slower and slower and slower. So what does that look like mathematically, or more importantly, graphically? What does that look like? How does it look like with the fact that the current is charging up really fast at first, but the more charge I get in there, the slower it's going to charge up? Or more importantly, how does the voltage look? So I'm going to give you a graph of how the voltage looks. The more charge I have in the capacitor, the more voltage I'm going to have across the capacitor. So here's a very important graph. So this is time. And for now, we'll say this is volts. Now, when I have a capacitor, this capacitor can't charge any higher than this voltage source. We said this was 10 volts, so this can only charge up to 10 volts. If this was 100 volts, this can go up to 100 volts. It can't get any higher than the source voltage. So let's say that this line right here represents the total voltage. So this is VT. This is VT. That's the highest that capacitor is going to charge. This is time. So when I close the switch at T0, this is T0 right here. T0. What's going to happen is that capacitor is going to charge up real fast at first. It's going to charge up really fast, but then the more charge I get into the capacitor to add more voltage, the harder it is for the next one to get on the plate. So it's going to charge out, start out real fast, and then it's going to level off and go slower and slower and slower and slower. It's going to look like this. But eventually, it'll reach the total voltage and it'll stay there. Well, when it reaches the top, let's say at this point right here, it reaches the total voltage. That's called steady state. Steady state. It's after here is steady. It doesn't change anymore. But if I drop a line down here, what happens is for any kind of capacitor, it takes 5 of these to completely charge. And I want to say that a second time. For any capacitor, I don't care what value I have here. It doesn't matter. It's going to take 5 time constants to fully charge. So let me show it like this. The product of R and C. The product of R and C, R times C is tau. For the problem right here, we said it was 10 seconds. That's what we calculated. So the rule is it's going to take 5 time constants for any capacitor to charge up. So I can divide this between this point and where it's fully charged. I can divide that into 5. This is 1, 2, 3, 4. Here's 5. So here's tau. This is 2 tau. This is 3 tau. This is 4 tau. This is 5 tau. All capacitors take 5 time constants to fully charge. Well, since we know the value of R and C gave us 10 seconds, what we really mean is this is 10 seconds. This is 20 seconds. This is 30 seconds. This is 40 seconds. After 50 seconds, this capacitor was fully charged. Now this is actually pretty cool because what I can get any time here I want by picking the proper value of R and C. Anytime I want, which means I can control how fast or how slow this capacitor will charge up. So what might I use this for? Well, any kind of timing application, to time anything, I can use something like this. So this is used in a whole bunch of different areas, more than I care to go into right now. Now, how does this apply to, like, what kind of problem would you have to solve with this? Well, when the capacitor values are changing like this, in the first examples I gave you in the homework, we calculated the voltage across each capacitor. Well, once we found the voltage was 20 volts, it was 20 volts. It didn't change. But here things are changing depending on what time you look at the circuit. I mean, if I look at it at 10 seconds, I got this amount of voltage. But over here at 40 seconds, I got way more voltage. And by the way, just so you can see this, if the voltage is going up like this, then the current is actually decreasing like this. It starts out really high, and it's going to take 5 time constants, and the current will completely stop. So the red represents current, but you just focus on the purple right now, which represents the voltage across the capacitor. I actually put this graph on Blackboard. There's a printout of this. If you look at those documents up there, there's a graph. This is called the universal time chart. You don't have to worry about the name, but this you have a printout of this. But I want you to understand how this works because it has so many applications. So what we got to be able to do is, if I got a graph and I know what the RC time constant is, I can give you, like, say, all right, give me the voltage at 20 seconds. You say, all right, I come over here, it's so many volts. It would be nice to be able to figure out what the voltage in the circuit is or the current in the circuit is without using the graph, by using equations. And so I want to end today's session by listing those equations on the board, and then next time we get together, we will we'll talk about them. But don't sign off yet when I'm done, because I got a few things I need to talk about the lab. I think you guys got an exam out there that I need to get turned in. So before you sign off, I want to talk about those a little bit. How we're going to handle the lab since you're remote, and how we're going to turn in the exam. So I'm going to talk about that. But let me give you these equations, and we'll put them on the board, and then we'll talk about them next time. So I can use this graph, or I can use these equations. So just write it down, and I'll explain it next time. So I got 2 sets of equations. One is for capacitors charging. This is capacitors charging. And I got capacitors discharging. Now, I don't know if you can see up there, it might be some glare. It says caps discharging. And so I got 2 sets of equations. So I got to first determine, is my capacitor charging or is it discharging? Well, clearly, when I close the switch, it's going to charge up. But if I wanted to, I can put another switch over here and run a wire down here like that. And if I close this switch, it will charge the capacitor up, and I can open it up. If I close this from the discharge capacitor, then I can open it up after it's discharged. So you got to figure out if I have a charging circuit or discharging circuit, but we'll do that next week. Don't worry about that right now. Let me just give you the equations. So under charging, I'm actually going to just use the whole board. So for capacitors charging, I can find VC, VR, and I. And that's for this simple circuit that I just had on the board, where I had a switch, I had a resistor, and a capacitor. VC is the voltage across the capacitor, and VR is the voltage across the resistor. So I can find that like this. This is equal to V total times 1 minus e to the minus t on tau. Now this e thing, it's this is the e to the x. If you look on your calculator, you have an e to the x key. You should have an ln key, and near that, you'll see an e to the x key. So that's what that is, e to the x. So it's Vt, this is Vt, times 1 minus basically e to the x. But again, we'll do some calculations with this next time, and I'll make it crystal clear. I just want you to get the equations. VR is just Vt divided by R times e to the minus t on tau. Actually, that's not right. Don't write that down. That's this one. VR is just Vt e to the minus t on tau. And then this one, I, is Vt over R times e to the minus t on tau. Now, if you can't see this, it's okay, because this is actually on the handout that I put on Blackboard for you. You'll see these three. But this is for capacitors charging. And we'll do an example of this next class. On the other side is, what if I have a discharge circuit? What would that look like? Well, let me put those up here. If it's discharging, VC equals Vt e to the minus t on tau. VR equals Vt e to the minus t on tau. And I equals Vt over R e to the minus t on tau. If you compare these, this and this are exactly the same, and this are exactly the same. So the only one that really matters, the only one that's different, is the one for the capacitor. VC is for the voltage across the capacitor. If I'm charging the capacitor, it looks like this. If I'm discharging the capacitor, it looks like this. So again, we'll do an example of this next class. For now, I just want you to focus on this sheet I put up on Blackboard. And I actually forgot to put one up. I'm going to put up another sheet that has some word problems on it where you can use that other. I don't know. I'll think about that. I might bypass that. You guys probably got enough to do. Now I'm going to want to end the session now. Does anybody have any questions for me? Anybody have any questions over any of this stuff that we talked about so far? Okay. Well, let me talk about two things. First, you have the exam that needs to be turned in. You've had it for a long time, so hopefully you've been working on it and got it complete. I'm going to collect that on Saturday. I need that turned in on Saturday. The way you're going to turn it in is I need you to turn it in. You can I can't think of the name of the app. I'll give it to you on Blackboard, but there's an app you can use to take a picture of it. It will turn it into a PDF. I just can't think of the name right now. You may already have something that will do that. If you have a scanner, you can scan it into a PDF. You can do that. But if you can't scan it to PDF, I'll give you information on this app you can put on your cell phone. You can take a picture of it. It cuts out the background and turns the paper into a PDF. You just got to make sure when you take the picture that you look at it, I got to be able to see your work, all your work. There'll be a link on Blackboard for you to upload it on. And I'll send out an announcement. It'll take you to the link, you upload it, and I'll be able to see the PDF file. Again, I'll make that due on Saturday, let's say Saturday at midnight. So hopefully you worked on it and got it all worked out. But if you don't, between today and Saturday midnight, go ahead and get it done. The lab. So right now, you know the school's going to be closed for the rest of the semester. We still got to do labs. So I'm going to give you a sheet that allows you to go to a website to download software, simulation software called Multisim. Let me write the name on the board. Multisim. And this is an electrical simulation software. It'll allow you to build circuits with resistors, voltmeters, just exactly what we would do in lab. You can do it with this software. So you're going to use simulation software to build your labs. And then you will submit these to me via the same way you deliver your exam. I'll have you put it in the form of a PDF. You'll upload it back to Blackboard. So what I'm going to do is this. Between now and sometime tomorrow, I'll give you information. I'll put a lab folder up on Blackboard. And in the lab folder will be the information you need to get Multisim. You should be able to download it for free. They gave us a free license that you can use to the end of the middle of June or something. So you'll be able to download the software. And I'm going to give you a tutorial. Between the tutorial and YouTube, I want you to become familiar with this program, Multisim. Then I'll give you a lab, a Multisim lab to do for practice. You'll turn that in for credit. And once you turn that in, I'll give you other labs, and this will suffice us to the end of the semester. So look for two things. Number one, a link to upload your exam to by Saturday night, midnight. And number two, I'll put a lab folder up there. It'll have all the information there for Multisim, how you download it, and all of that. Don't wait till the last minute to do this. I had some guys in the other class. They have a lab due. It was today at 1. They had this thing for over a week, and they decided to wait until today to do it. Then when they tried to download Multisim, they had issues with it. So I'll give you the information between now and tomorrow. Go ahead and download the Multisim. Get it installed, make sure it's running, try to play around with the tutorial, and then once you know it's running, you're not having any issues, then you can do the lab before next week, before next Wednesday. The lab will be due next Wednesday. The exam will be due Saturday by midnight. If you have any issues with Multisim, well, first of all, if you have a Chromebook or an Apple computer, I don't think this will work with that. So if you have an Apple computer or Chromebook, send me a text. Let me put my number here. That's 513. So if you have a PC, you shouldn't have any problem. It should work just fine. But if you have an Apple computer or a Chromebook, let me know by text, and I'll call you sometime either the next couple of days. And I'll show you another way to connect to this Multisim if you have any issues with connecting to it from the free download that I give you. So I think that's it for today. Does anybody have any questions for me before I leave this session?
When do you want the homework turned in by?
I'll put due dates on the homework. Some of the homework, if I already have a space for it on Blackboard, you can't upload it. I need to see how my Blackboard is laid out. Honestly, I don't remember. I got too many classes. So I'll do that between today and tomorrow. If there's already a space for it in Blackboard, you're going to have to scan it and email it to me. Because what I have to do in Blackboard is create a special column that you can upload to. So if I already have a grades in there for, let's say, homework 3, and half the class turned it in, I can't make a separate column for that homework 3. So I'll let you know by do this. Text me what you have homework outstanding, what you have to turn in. And I'll tell you how to turn it in. So just send me a text, the next day or two. Say I have homework, whatever. It's the sheet on series parallel, whatever it is. Explain to me what it is, and I'll tell you how to submit it. Either it's going to be an upload or it's going to be an email. That's the best way to handle that. Does anybody else have a question? Okay, well, if you have any issues or questions, let me know. Text me. You can email me, but the quickest way is to text me. Hopefully you guys are staying safe. It's starting to get really scary out there. I don't even turn the news on because the numbers are going up, and I'm already got these issues I'm dealing with, anxiety issues. And so it's a crazy world we live in. Just make sure you stay safe, and I'll see you guys at the same time next week. We'll get more into the capacitor stuff and inductors and more into the AC. Any issues or problems, just let me know by text or email. You guys stay safe, and I'll see you next class.